Okay, we've reached the end of our travels pretty much. Today we'll finish up on low pass and high pass filtering and go into maybe band pass and stop pass filtering. So let's get started. We'll go first to our PowerPoint presentation. And here we are. Let's go to the slideshow and slideshow from the beginning. Okay, here we go. So this will finish up our chapter 26, sections 9 through 12. Okay, and in that, so we will first review a little bit about the low pass and the high pass filtering, look at series RC filtering and series RL filtering. Then we'll look at some filtering on small frequency band. So basically we're interested in choosing a small interval of frequency, which we call a band pass filtering. And we can use that as a band pass filtering, or we can use it as a band stop or band notch filtering. Means we want to discard that particular range of frequencies. We'll take another look at the designating power. How do we do that? And introduce ourselves to a decibel system. Look at some graphing, okay, over a large range. And then we'll talk about resonance filtering circuits. Okay, so let's look at RC circuit, where the output now in this case is a output directly from the capacitor. That gives us a low pass filtering as pictured by this Bodie plot here. So anything at low frequencies here pass, and then once they go any frequencies beyond the corner frequency, you notice that the slope diminishes by -2 dB per decade. We will talk about what dB stands for, okay? But it basically attenuates. This signal is not, the signals down in this range are not strong enough to be carried forward. If we take, on the other hand, instead of looking at the output from the capacitor, we take a look at the resistor output by just switching the resistor and capacitor around, we get the opposite effect. And here we get low frequencies are blocked, but high frequencies are passed. So again, we have that same slope of about 20 dB per decade, okay? And our specific frequency occurs, the cutoff frequency occurs at -3 dB. dB stands for decibel. And switching to RL circuits where the output to the L side, in other words, our output here is going to be across the inductor. And we can see that this gives us a curve very much like the output from a resistor in an RC circuit. Okay, so basically what that means is an inductor actually passes high frequencies and attenuates low frequencies. Okay. We can look at the phase shift of what happens. You can look and see it right where the cutoff frequencies occur. Our phase is actually at plus 45 degrees. Okay, so that phase shift at 45 degrees corresponds to where the shift is from essentially stop to pass, okay? And if we switch those two around, then we get the opposite picture again. But still, we get the phasing angle changing in such a way so that at 45 degrees, we get that cutoff position. So basically, these are just basically little schematics on the different ways we can have a low pass filtering and high pass filtering, okay? Whether we use an RC or an LR or RL, or here again, RC and RL circuit. So RL and RC circuits consistently work opposite to one another. So how do we do a bandpass filtering using an RC? Well, we have an input signal of multiple frequencies, okay? So we want the output signal also has a range of frequency between low and high. So we want the lower frequencies above and the higher frequencies below FC. Okay, the strategy here to create this is to first pass the high frequencies, so get past all those high frequencies, and then use a filter for a low pass filter to just get rid of the frequencies that you don't really want. What that looks like is just as we see here, we've got a high pass fee, we got our voltage in, pass it through a high pass filter, so it gives us a range of high frequencies. And out of that range, then we cut off the lower frequency ones that we don't want. Okay. So we've got, in this case, for the high pass, our cutoff frequency is given to 1 over 2 pi R1 times C1. And the high frequency is 1 over 2 pi R2 C2. Okay. And what we get then is our low cutoff and our high cutoff, but in between the low and the high cutoff, we get a bandpass for a bandpass filtering. Okay, the difference then the bandpass range, okay, is the difference between the two high and low frequency cutoffs. The opposite is true if we want a band stop, or what we call a notch filter, right? So basically we're going to, between the lower frequency and the higher frequency, anything between those frequencies, we stop it. We essentially drive it to ground, okay? Or its amplitude is so low that it just doesn't it doesn't affect anything. So again, to take a look at it, we pass low frequencies and we pass high frequency, but we stop those mid-range frequencies. How do we design it? In this case, we're going to use a parallel circuit. So we're going to put a low pass filter in parallel with a high pass filter. Okay, and that parallelness was going to give us the band stop that we desire. Okay, so that's what we look at. Okay, and we can see here we've got a high pass filter. We use a particular T-type filtering system. This is in the form of a T with 2 resistors and a capacitor. and a low pass filtering using 2 capacitors and a resistor, okay? Because these have an opposite effect, okay? So that's how we use the, whoops, the high pass filter in parallel with the low pass filtering. So the notch has a frequency of 1 over 4 pi R C1, okay? And our output will look very much like that. So there's our critical frequency. That's our frequency that we're going to stop. And those are our 2 boundaries, the low cutoff and the high cutoff frequencies. So how do we designate power? Okay, power levels really have a very large range. We can go from milliwatts up to watts, mid-range, kilowatts, and megawatts if we're talking high power systems. So these are 4 orders of magnitude and range in power as a designation. Okay, so if we wanted to plot some of this stuff, it's kind of hard to do it in our usual linear plot, or because linear means 1, 2, 3, 4, 5. That's a linear range. It's but we use a logarithmic scale, and we're talking powers of 10. Okay, and here we're talking about powers of 10. So from milliwatts to watts, that's a tenfold. To kilowatts is another tenfold, and it keeps going up. Okay. So power decibels, dB stands for decibel unit. Definition, it's used to measure the intensity of the sound or the power level of an electrical signal by comparing it to a given level on a logarithmic scale. So basically we're talking about a logarithmic quantity. Okay, why do we like logarithmic? Well, it goes back to this. We've got a large scale, so we want to use a logarithmic scale. So the math definition for a decibel is it's a number, is for a decibel 10 times the logarithm of the ratio of the output power to the input power. Okay, so we want that to be, if it's P is higher than Pn, then we've got a positive number here. If P out is smaller than Pn, then we get a lower number. We get a negative number because it's a logarithmic. So P out is the output level, Pn is the input level, and P out per Pn is the power level increase or decrease. So basically what we're talking about is a degree of loudness. How loud can you get? Okay, is it deafening loud or is it very quiet loud? Okay. So again, our decimal number is 10 times the logarithm of the ratio of P out to Pn. So if N is greater than 0, then power is gained, and we got the signal is amplified. In other words, it gets louder. If, on the other hand, that number is a negative number, it's below 0, then we get a quieter situation. So the signal is reduced, or we say it's attenuated. All right, so how does that go along with voltage levels? Okay, for RC, okay, we're going to use low pass is 20 times, not 10, but 20 times the logarithm of the voltage output to the voltage input. Okay, so basically it's going to be 20 times the logarithm of, for RC, it's the capacitive reactance divided by the impedance. For high pass, it's the ratio is the resistance to the impedance, always 20 times the logarithm. Because you remember, we want low pass, we use across the capacitor. If we want high pass, we go across the resistor. And conversely, for the RL, okay, we use the opposite. For low pass, we go across the resistor, compare it to the impedance, total impedance. But for high pass, we use the inductive reactance and compare it to the total impedance. And attenuation at FC then gets to where we're using 20 times the logarithm of 0.707. And if you recall, that number is the half power unit, okay? That's the half power unit, 0.707 of your maximum. So 0.707 represents minus 3 dB. And if you ever saw a loudness meter that's used in recording, you'll notice that on the meter itself, you've got plus 3 dB and minus 3 dB. And the needle goes back and forth so that you can change the loudness to where you want it to. You want it usually around the 0 point, okay? So graphing. Graphing we can use, we don't really, right now we use computerized graphing, so we don't use graphing paper much anymore, but we can. We have the log-log graphs giving logs in the x direction and in the y direction. So basically what that means is we'll have numbers 10, 100, 1,000. So basically it's 10 to the 0. We can always start at 1, which is 10 to the 0. Then we go 10 to the 1, 10 squared, 10 cubed, 10 to the 4th, so on. Or we have a second semi-log where one of the axes is linear, 1, 2, 3, 4, 5, and the other is logarithmic, 10 to the 0, 10 to the 1, 10 to the 2, 10 squared, 10 cubed, and so forth. Okay. Why we do that? Well, here's your range of frequencies. We got a huge range of frequency. Okay. Extremely high frequencies are those frequencies that are above 300 gigahertz. Okay, gigahertz. And we got super high frequencies, stuff that's between 30 gigahertz to 300 gigahertz. Then we go to ultra high and so forth. And then we go all the way down to extremely low frequency we get down to 3 hertz, which is very low. Okay. So that's just the frequency range. And logarithms are numbers expressed as 10 to the x, so the log of 10 is 1. So if we got log a to the n, we know that that's equal to n times the log of a, okay? So for example, if let's say a is 10 to the 3rd, log of a then is 3 times log of 10. Log of 10 is 1 because 10 to the 1 power gives you the log, it gives you a log of 10 to the 1, meaning it's 1. 1 times 3 is 3. If you use 10 to the minus 3, then you get a minus 3, or log b. We can also use the natural logarithm number, which is 2.7183. Okay, that's our natural number. So we can use natural logarithm of a. But in electronics, we rarely use that because we're usually working in the engineering units. But if we were to plot a graph, okay, for example, log to the base 10 of fx, okay, is equal to minus 2 log to the base 10 of x plus 4, we get a straight line when we plot it on a log-log scale, okay? There's no 0 because the solution to log x equals 10, 0 doesn't occur because x has to be minus infinity, all right, for that to work out. So if we use RC low-pass filter, your normal graph would look something like this, where we've got a frequency range from 0 to 5,000, okay, and that's our output that looks like that. And that's a voltage output. If we put it on a semi-log, okay, where the output is in a semi-log, is a logarithmic, we haven't changed the frequency, then we flatten out the curve somewhat, okay? We almost make that almost straight, almost linear. But if we use a log-log scale, then we get a nice curve, and basically we've got logarithm for the voltage output and logarithm for the frequency, okay? And then this is often done because the frequency range, it can be huge, okay? And if that could be huge, so can the output be very big. So voltage is displayed as the log of V out, and frequency is also displayed here as the logarithm of frequency. So we want to be able to use resonant circuits. Now last week we talked about resonant circuits, and we know that we create a tank circuit, it creates a certain resonant frequency, which is a good filtering system, okay? It basically allows us to choose a very specific frequency to pick up a signal that's a specific frequency. Well, in the case of a series resonant circuit, we maximize current at that resonant frequency. But we have a very low impedance, okay, which means it's basically 0. So it's non-existent. You got no resistance essentially. But in the parallel case, we maximize the impedance at FR and minimize the current, okay? But there is some current there, okay? We can actually later on amplify so that we can use the parallel circuit as a tuning circuit. So we can use series resonant filtering, okay, basically by using, we take the output from across the resistor, and our resonance is through here, through ALC series, or we can use a band stop filtering by getting an output across our serial LC circuit, okay, avoiding R. And we can use a parallel resonant filtering as well. Here's our tank circuit, okay. We get resonance here. Again, we have the output is across the resistor. Again, here, the output is across the resistor for bandpass filtering, which we add an RS value as well. Okay. The low frequency RL is shorted by low resonance reactance of L and higher frequencies. And the low reactance of C shorts out RL. Okay. So there you go. And then finally, we have pi and T filters. Okay, T filter, you can see two capacitors and an inductor. Pi filter is two capacitors and an inductor in series between the two. Okay. And that's it. Now, one thing I've done for today actually is I've given you a quiz. Okay, I've given you a quiz to kind of balance out any low marks that you got on the exams. Okay, the quiz is straightforward, pretty simple. 20 questions, do all of them, and each question is worth 5 points, and they're straight from the book. Okay, you should be able to get close to 100%. Okay, and it'll help your grade. Okay, and also, though, it also goes over some of the more important points that we've gone over for the past 2 weeks. Okay, so good luck on that. Don't forget to hand it in. Okay, so if you want a grade, hand it in. And that's it. So good luck. And tomorrow we will have a final. And I'll give you special notes for tomorrow as well, on tomorrow.